So this is kind of what we're going to get into today. So this is polarizing film, okay? And so what polarizing film is, it's a series of very small fibers that have been embedded within this film. So if I lay one up there, okay, cool, right? So if you view light as a wave, what this is doing is that it's only allowing light waves that are basically, you can think of it as like that fence. You can think of it as what it's letting through is the light that's parallel with those rays. Now, if I take this like this and overlay it, you can't tell any difference, okay? Light just goes through. But if I turn this thing 90 degrees, I block the light. Because what's happening here is that with this one, now, instead of being parallel like this, now it's at 90 degrees to each other, and it's blocking that. So if I go somewhere in between, like that, okay, then some of that's going through. If I turn it where it's all parallel, you can't tell any difference at all, okay? So that's the fundamental difference between these. So if you look at, and if you have like polarized glasses basically block light that is at a certain wavelength or certain direction relative to your incoming light that you see. Now, the other thing that can happen is that sometimes different materials get a little bit wonky. So this is just your basic protractor. And if I put that up there with just one polarizing film, not a lot happens. But if I overlay it with that second polarizing film, you notice that it gets a little bit weird in terms of colors. Because what's happening is that as that light goes through that first piece of plastic, it gets twisted. And so what the second piece of, this is why you can't see with just one piece of polarizing film. So materials that are optically active, basically they take that light and they twist it. So then when I put that second one over there, then you're basically sorting it based upon those colors or the light that's made it through a particular set of gratings, and then you can twist that light. Now, corn syrup is also optically active. So, put this up like this. Those are just air bubbles in there. It's not like a biology experiment, not bad. So, but if I put this up here, because corn syrup is very optically active, you get these weird colors when you put over that second polarizing film. Because again, the light goes through, the first grating hits that corn syrup, it gets twisted, then I can twist it again based upon that second piece of polarizing film. So here's the cool thing about light, and you're going to see this. Sometimes we're going to treat it as a wave, sometimes we're going to treat it as a particle. If light was just particles, this would not happen. Okay? If light was just a particle, then if I did this with just your straight polarizing film, it wouldn't make any difference which direction I put it, because it would be like shooting marbles through there. Okay? If I'm just shooting marbles through there, and if I twist this, nothing's going to change. But, because all the marbles are still going to go through. But since it's a wave, when I twist it, that's what makes the difference. Got that? Okay. So, Jane, here's your test. Okay, so that question was missed quite a bit. That was the only one that was kind of missed most. When you get to that second to the last question, or question number 4, where you had like the two sources, and you had to figure out the whole key to that is that you want to hear where there's a minimum, okay? Well, the equations give you that delta x equals m L lambda over d, that gives you distances to maximums, okay? So that was one of the key things that you had to understand. So when you got to question C, some of you made the C so god-awful complicated. All it says is identify another location on the line that passes through P and Q where the student can stand in order to observe a minimum. Here's the easiest way to answer that question. This is symmetrical. So if you know how far it is to one side, guess what? There's just a matching one on the other side. That was the easiest way to answer that question. Literally, that's all you had to say. Take your answer from B, say, hey, we're going to stand on the other side of that because this thing is symmetrical. Or you could add, like, in effect, like a one of the like the whole value to it and get that distance that way if you wanted to go another, like, fringe down. Okay, but like I said, if you want to do the test corrections, you can. If you're happy and you know it, clap your hands. So, there you go, whatever you want to do. All right, but like I said, the tests are in the grade books. You can see exactly what you have going on. Okay. So, here's the next big chapter. And this is what we call ray optics. Okay? Now, ironically, even though I just went through this whole thing of talking about how light travels as waves, when you do ray optics, you actually take it as traveling as little, like, bits of matter that travel in straight lines. Okay? So this is why, depending on how you view light, sometimes you want to view it as a ray, sometimes you want to view it as a wave. Kind of depends on the situation. So we're going to deal with a couple of things. We're going to start with, initially, flat mirrors. Okay? Now, y'all have stood in front of mirrors before, done your hair, brushed your teeth, whatever. Okay? You stood in front of mirrors. But let me kind of get, and again, I'm going to tell you right now, Cohen, especially you listen to this. Don't think about this too much or you're going to end up in the corner doing drugs. Okay? Because it's going to kind of alter your perception of reality. Okay? Just a little bit, not that. So, what we're going to do is that I'm going to use, Danny, we'll try and just kind of turn it and face it towards that window.
Okay, got it.
Okay. So, let me go. And we're going to try and use that glass as a mirror. Yeah, that makes it easier to see. Okay. So, here's the drill. What has to happen for me, what physically has to happen for me to see myself in that window?
Light has to bounce off the window into your eye.
No, that's like way down the line. That does have to happen, but that isn't the first thing that has to happen.
Light bounces off the window.
No, that's further down the line.
Really?
Light bounces off you?
Light bounces off me,
Oh, yeah.
right? Because if the light doesn't bounce off me, guess what?
You
It doesn't bounce off the mirror. So photons get emitted from the light. They hit me, a shirt, okay, and then they bounce off, and then they hit the glass window. Now, some of that goes through, some of that gets reflected back. So it's got to go from the light to me, to the mirror, off the mirror, back to me. Okay? So it's kind of a bit of a journey that it has to travel. Now, this is where this gets a little bit weird. Okay? So, if I raise my right arm, okay? So raise my right arm. imagine, if you will, that there is, God forbid, a twin of me on the other side. Okay? So there's an identical of me on the other side. And we're going to play a game that they're going to try and match everything that I do. So imagine that that's just you, that none of that light gets reflected. But we can see the twin of me on the other side. Okay? So if you're the twin of me on the other side and you're going to try and do what I do, if I raise my right hand and you're the twin of me on the other side, what are you going to do?
Left hand.
You're going to raise your left hand. Okay? If I raise my left hand, you're going to raise your right hand. Okay? If that was an actual pure mirror, I could not tell the difference between if that light was being reflected off of me, and this was happening, or if there was a person just like me on the other side mimicking everything that I do. Okay? So when you look in the mirror in the morning, go like, is that a reflection or is there another person just like me on the other side? I don't know. Kind of weird. But now, if I am 3 meters away from the mirror, if this is going to be symmetrical, how far away does my twin have to be? 3 meters. Okay, so if I'm 3 meters away, the light hits me, it's going to travel how far? 3 meters. But then it's going to bounce off and travel 3 more meters. Okay, so it's got to travel 6 meters. All right, boom, there you go. Now, right now, let me see. Jane Carroll, can you see me?
Yeah.
Okay? And I can see Jane Carroll, right? So, now what's happening is that light's bouncing off me, going there. Now, the same thing is happening to Jane. So, I can see Jane, Jane can see me. Cool? Now, I'm going to come up here. Jane, can you still see me?
Yeah.
Okay, now, I'm going to move over here. Can you see me, Jane?
No.
No. Guess what? I can't see Jane. Okay? Why can't I see Jane? But if I move over here, I can see Jane. Now, Jane, can you still see me?
Yeah.
Okay? Still see me?
Yeah.
But now, can you see me?
No.
So here's the deal. If I can't see Jane, Jane can't see me. But if I can see Jane, now, if you'll notice, from my perspective, I can't see myself in the mirror. So where I'm at right now, I can't see myself in the mirror. But I can see Jane. Why? Oh, it's an angle. Oh, maybe a little geometry thrown in here. Whoa. Now, what we're going to talk about is what's known as the angle of incidence and the angle of reflection. So, if you imagine light being like ping pong balls. So, if I'm going to see Jane, basically what happens is this. That light's going to come in, it's going to hit that glass like a ping pong ball, and it's going to bounce off, and it's going to hit me. So, if I can see Jane, even though I can't see myself, Jane can see me. I can't see myself in the mirror, but I can see Jane, because Jane can see me. Now, if I move over here, way over here, what's going to happen? Jane can't see Jane. Now, what if I move way back? Okay, Jane, can you see me?
No.
Okay? Now can you?
Yeah.
Okay. But now, if I stand back behind Jane, and if I stand over here, okay, Jane, can you see me?
Yeah.
Okay? Can you still see me?
Yeah.
Can you still see me?
No.
Now you can?
Yeah.
Now you can?
Yeah.
So imagine, now we're at an angle. This isn't in a straight line. So that light is going from Jane, hitting the mirror, and then bouncing off me. So if that's a flat surface, what do you think is true about the angle of incidence and the angle of reflection? Ah, they're equal. Okay? They're equal. Now, if I move over here, Jane, tell me when you can't see me anymore.
I can't see.
Can you see me now?
No.
Yeah.
Okay? Because guess what? Now I can see Jane. So here's the point. If you're going to see something in a mirror, here's the rule. If you can see something in a mirror, it can see you. Now, if you're ever, when you're driving, and this is a pet peeve of mine because I tend to drive big trucks and haul trailers. If you're behind a semi or somebody driving a trailer, and if you're right there behind them, and if you can't see their mirrors, guess what?
They probably won't see you.
They can't see you, okay? So if you're driving behind a large vehicle, okay, and oh, I'm just gonna get right up behind him and tailgate him, okay?
No, that's gonna
Oh my
influence.
God, okay? You're gonna send me in a fit of rage, do that, because here's the story. Guess what? I can't see you because you can't see me. All right. Okay. Now, hold on.
Visibly the vehicle, so.
Now, so we've talked about index of refraction, right? So index of refraction causes light to bend. So I'm going to pass this around, and what you want, you can just look at your hand and just tilt that, and what you'll see is that even though you're still looking at your hand, like if I hold this up, to me it looks yellow, but if I turn it a little bit, then part of my skin looks yellow and blue. If I turn it a little bit more, then it appears red. So all of this is happening because light is hitting my hand and bouncing off. What changes is how that light interacts with this crystal. So as it travels through this cube, it alters the light. If this was just a completely clear cube, you would see some distortions because of the fact that it has a higher index of refraction than air does, and that light's going to get bent. So it's just kind of cool. So I'm just going to pass it around, just hold up your hand, and then you can just twist that thing, and you can make like your fingers appear to shift, and they can appear to change color. So. Okay.
Please don't get that. You keep fun of me. You're the same for me.
No.
Me and you are, me and you come in the same colossus.
Okay. So this is what's known as Snell's law. And we're going to also go out to the fish tank, and I'll show you this on a little bit bigger scale. So Snell's law plays out when you have light going from different optical mediums. So in this situation, this is what we're going to do down at the fish tank. So I'm going to shine a light from air, which basically you're going to assume that air has an index of refraction of 1. And this is going to be the sine of the angle. So that angle is always defined relative to what we call the normal. So imagine a vertical line that's here, And that's where you're gonna measure that angle from. It isn't from the horizontal, okay? It's always measured from the vertical. So we're gonna shine this thing into water, which is a higher index of refraction. So because it has a higher index of refraction, what do you know about the speed of water, or the speed of light in water versus the speed of light in air?
Slower.
It's gonna be slower, okay? So this is going to be slower. So here's how you can, and I kind of gave you this example before, but now we'll kind of expand on it a little bit. So imagine that this is your car axle with a set of tires. The bigger that index of refraction is, the more difficult it is for your car tires to travel through it, okay? 1 is absolutely your best case scenario. That's dry pavement, that's when you can go the fastest. The bigger this number is, the harder it is for your car to go through it, okay? So, imagine this is coming through here like this. Now, this side, imagine this is this axle, okay, like this. So imagine there's your car tires. So as that hits, this side right here is going to hit first, okay? So since that side hits first, what's it going to do? It's going to bend towards the vertical or away from the vertical. Andrew,
Towards,
why?
because the wave hits the closer side to the water first, which slows it down, but the rest of the wave outside the water continues on at the same speed, which pushes the energy in a slightly different direction.
Beautiful, okay? If you want to think of it as a wave, and just if you want to think of it in terms of the axle in your car. This tire, this side of the wave, whatever you want to think about it, is going to slow down first. The other side keeps going, okay? So that's going to slow down, that's going to go like this. So from a conceptual standpoint, you can make the argument that when that hits, that angle should get bent towards the vertical, okay? Now, mathematically, okay, here's where math to the rescue. So if you look at that n, which is 1, times the sine of 30 degrees, is going to equal n2, which is 1.80, times sine theta 2. So how are you going to get sine theta 2 by itself? Yeah, take 1 times the sine of 30 divided by 1.8, and then take the inverse sine, right? So somebody do the math, and make sure you're not in radian mode.
16.13.
What'd you get, 16 point?
13.
So call it 16.1 degrees. So notice that, because it's the angle with the vertical, not the angle with the horizontal, that angle became smaller because that got bent towards that. Now, if you reverse the process, so now, let's say here's that glass of 1.80, and it's at 16.1 degrees. That's a horrible end. And this is air, right? So, if you look at it from this perspective, you're going to go from where you have a very slow medium to air. So what's going to happen here?
Speed up.
Which side? As this is coming into air, this is your dry pavement. When this comes into that dry pavement, what's going to happen? My thumb side is going to speed up or slow down. It's going to
Speed up.
speed up. So it's going to go more like that. So if I go in this direction, it should go like this. And again, you can do this mathematically. If you take 1.80 times the sine of 16.1
That's
equals 1.00 times the sine of
where this
theta, what are you going to get theta to be? 30 degrees. So this became a bigger angle. Okay? So you got the visual mathematically. Okay, stop you on the camera. Let's go down to the fish tank.